Right now, without you feeling a thing, you're moving. Not just spinning with the Earth, not just orbiting the Sun. Our entire galaxy, all 100 billion or so stars, is being hauled through space at about 2.2 million kilometers per hour. That's 600 kilometers every single second. In the time it takes to read this sentence, we've traveled farther than the distance from here to the moon, and we're not drifting at random. We're aimed at one specific spot in the sky. You can't see it. Point the best telescope on Earth at that patch of sky, and you'll find almost nothing looking back. No blazing beacon, no obvious object big enough to explain the force. And yet something out there has a grip on us, and it isn't letting go. For decades, nobody even knew the pull existed. The sky looked settled, evenly spread, going nowhere in particular. To understand where we're being dragged, we have to go back to when astronomers thought the sky was perfectly calm. In the 1920s, astronomers pointed their telescopes at faint smudges of light and started measuring how fast they moved. The trick was the spectrum. When a galaxy races away from us, its light stretches toward the red end, and that shift tells you the speed. Edwin Hubble and others read those shifts one galaxy at a time. The pattern that fell out was almost eerie in how clean it was. Nearly every galaxy they measured was moving away from us. Not just some of them, and not in one direction, but spread across the whole sky in every direction you could aim a telescope. And the farther away a galaxy sat, the faster it seemed to be fleeing. Double the distance, double the speed. That simple relationship became the backbone of a brand new picture, a universe that wasn't sitting still at all, but expanding, carrying everything apart like dots on an inflating surface. It was tidy, it was predictable. You could measure a galaxy's distance and guess its speed before you even looked. That neat picture had one number in it that refused to behave. Edwin Hubble noticed it in 1929. The farther a galaxy sat, the faster it appeared to be racing away, and the two numbers climbed together in near-perfect step. Plot distance on one axis, speed on the other, and the dots fell along a straight line. That relationship got a name and a number. Speed equals distance times a constant, the Hubble constant, roughly 70 kilometers per second for every megaparsec you travel out. Double the distance, double the recession. It was clean enough to feel like arithmetic, not astronomy. And that cleanliness did something to your intuition. A rule this tidy suggests the universe is playing fair everywhere, expanding at one steady rate, no favorites, no exceptions. You could trust the line to tell you where everything was headed. But a straight line through real data is never truly straight. The dots scatter a little above and below, and most of that scatter looked like ordinary measurement noise. Most of it. Beneath that clean line, a handful of galaxies were moving the wrong way. Point a telescope almost anywhere, and the story rhymes. Split a galaxy's light into a spectrum, and the dark lines where atoms absorb their signature colors shifted toward the red end. Hydrogen, calcium, sodium, all nudged the same way, like a familiar song played a half-step low. That shift is the fingerprint of retreat. The galaxy is moving away, and the faster it goes, the deeper the red. Turn to look the other direction, and the same thing greets you. Galaxies behind us, ahead of us, off to the sides, nearly all of them sliding away into the dark. For decades, that was the comfortable picture. We sat at the center of a great quiet withdrawal, every distant island of stars drifting off on its own tide, the whole sky exhaling at once. It felt settled. It felt uniform. But uniform skies don't hide surprises, and this one did. As the measurements piled up patch by patch, the retreat stopped looking perfectly even. One direction of the sky was hiding a pattern the others weren't. To make sense of any of it, cosmologists leaned on a single tidy idea. Zoom out far enough, and the universe should look the same in every direction. No special place, no favored corner, no cosmic center you could point to. They call it the cosmological principle, and it does more work than it sounds like. If matter is spread evenly, then expansion pulls everything apart at the same rate everywhere. Point your telescope any way you like, and the numbers should match. It's an assumption that made the math workable. treat the cosmos as smooth, and the equations that describe its growth suddenly close up clean. For decades, that smoothness held, at least at the scales anyone could measure. But an assumption is only as good as the day it survives. The principle predicted a sky with no preferred direction, no lean, no gentle push toward one horizon over another. Then a map of the whole sky's heat broke that assumption in half. When astronomers mapped the leftover heat of the Big Bang, the cosmic microwave background, they expected it flat, the same faint glow, 2.7 degrees above absolute zero, radiating evenly from every corner of the sky. What they found instead had a lean to it. One half of the sky ran slightly warm, the opposite half slightly cool. The difference was tiny, about 3.3 thousandths of a degree, but it was there, and it was steady, tracing a clean line across the heavens. They called it the dipole. Two poles, one hot, one cold, sitting on exactly opposite sides. A sky that was supposed to have no favorite direction had picked one, and it wasn't shy about it. That kind of pattern doesn't come from the early universe. The background heat itself is smooth to a staggering degree. So the warmth on one side wasn't the cosmos being lopsided. Something was skewing our view of it. Move toward a source of light, and it crowds together, shifts warmer. Move away, and it stretches, cools. The only thing that could tilt it was our own motion through the cosmos. So that faint tilt in the light wasn't noise in the instrument. It was a direction. Something out there was nudging the whole neighborhood, and once you notice a nudge, you want to know its source. This is the story of how we found that pull and then spent decades chasing it across the sky. It starts with a handful of astronomers staring at numbers that refuse to average out. It runs through a patch of sky we literally couldn't see, past claims that got named, disputed, and rebuilt. Every step forward meant measuring the motion of galaxies that don't hold still, sorting the tug of gravity from the stretch of an expanding universe. The mistakes matter as much as the wins here. More than once, the answer looked settled, then quietly fell apart. To get there, we have to go back to the moment before any of it made sense. Back when the maps were thinner and the pull was just a rumor in the data. Before anyone chased anything, our corner of space looked utterly unremarkable. Picture the Milky Way from the outside, a flat spiral maybe 100,000 light-years across, a couple 100 billion stars wound into arms, one yellow dwarf sun tucked about halfway out. Nothing about it stands out. There are trillions of galaxies, and ours is a fairly typical one. And the neighborhood matches the house. We sit in a loose cluster of a few dozen galaxies, most of them faint dwarfs you'd struggle to spot. No roaring quasar next door, no violent collisions lighting up the local sky. Just a quiet stretch of space that looks like countless other quiet stretches. For a long time, that was the whole story. An average galaxy in an average patch, coasting along with the general expansion. If you'd asked where we were headed, the honest answer was nowhere in particular, just outward with everything else. But the Milky Way isn't sitting still. It's drifting, and drifting fast, in a direction the expansion alone couldn't explain. For years, that motion read like noise, a leftover figure nobody could pin down. That drift was about to stop looking random. Before you chase a drift like that, you have to know where you're standing, and the Milky Way doesn't stand alone. We belong to a small huddle of galaxies called the Local Group, a family that stretches across roughly 10 million light-years of otherwise empty space. There are more than 80 members in this group, but only 3 that really matter for the weight. Our Milky Way, the Andromeda Galaxy, and the smaller Triangulum. The rest are dwarfs, faint little companions orbiting the big ones like moths around porch lights. These galaxies are bound. Gravity has knit them together tightly enough that the expansion of the universe can't pull them apart. While everything distant races away, our neighbors stay close, circling, leaning, held in the same slow embrace they've kept for billions of years. So when astronomers measured motion, they expected this little family to sit quietly, each galaxy doing its own private dance. What they found instead was stranger and harder to explain away. The entire group was sliding in one shared direction. Start with the one galaxy that breaks the rule. Almost everything in the sky is racing away from us, redshifted, fleeing into the dark. But Andromeda, our giant neighbor 2.5 million light-years off, is doing the opposite. It's falling toward us at about 110 kilometers per second. That sounds like a contradiction, and it isn't. Over short cosmic distances, gravity still wins. The pull between two massive galaxies is strong enough to overpower the gentle stretch of expanding space. So instead of drifting apart, we're drawing together for a collision billions of years from now. For a while, that felt like the whole story. Andromeda coming home, the local group bound by its own gravity, everyone's motion neatly accounted for. It's a tidy picture, and tidy pictures are exactly the ones that hide something underneath. Because when astronomers subtracted out all that local pulling, the numbers didn't cancel. There was a leftover push, a shared drift that Andromeda's gravity couldn't explain. Something far bigger than Andromeda was tugging on us at once. So step back far enough, and the universe stops looking like scattered dots. Galaxies don't fill space evenly. They line up along threads, thin, bright filaments of matter that can stretch hundreds of millions of light-years across the dark. Where those filaments cross, galaxies pile up into dense sheets and clusters. Astronomers call the flat ones walls, huge curtains of thousands of galaxies pressed into a single plane. Between them sit the voids, cavities tens of millions of light-years wide where almost nothing lives at all. Gravity built this over billions of years. Tiny lumps in the early universe pulled in nearby matter, then pulled harder, draining the gaps and feeding the crossings. What's left is a foamy scaffolding, empty bubbles wrapped in glowing strands, with galaxies flowing along the strands like water finding the lowest ground. And the flow isn't random. It drains toward the places where the threads tangle thickest, the crowded intersections where mass stacks on mass. At one knot in that web, the gravity was off the charts. So how do you even weigh a pull like that? You start with the one motion you already understand. Every galaxy is riding the expansion of space, drifting away from us at a speed that tracks with its distance. That's the predictable part, the steady current everything sits inside. Measure a galaxy's distance, and Hubble's law tells you exactly how fast expansion alone should carry it away. Then you measure how fast it's actually moving, using the redshift in its light. Line those two numbers up and compare. The gap between them is what astronomers call peculiar velocity. It's the extra shove, the part that expansion can't explain. Gravity from nearby mass, tugging a galaxy off the smooth Hubble track. The trouble is, distance is brutally hard to pin down out there, and one sloppy measurement can fake a signal that isn't real. So they leaned on standard rulers, objects whose true brightness they could trust, and averaged across hundreds of galaxies to beat down the noise. And when they subtracted the expansion, a leftover motion refused to vanish. Think about what that leftover actually means. After you strip away the tidy stretching of space itself, our whole neighborhood is still drifting, all together in one direction. Hundreds of galaxies, moving in step, like they'd agreed on it beforehand. They gave it a plain name, bulk flow, a coherent motion on top of the Hubble expansion that shouldn't be there at all. The numbers were staggering. Our local group, the Milky Way included, sliding through the cosmos at hundreds of kilometers per second, far faster than the smooth models allowed. That's the part that gnawed at people. Expansion pushes everything apart evenly, no favorites, no preferred direction. But this pull had a bearing. Something was tugging, and it wasn't scattered randomly across the sky. It was aimed. You can't shrug off a signal that survives that much averaging. The noise cancels, the errors wash out, and yet the drift stays, stubborn and pointed. That leftover motion pointed straight at a patch of sky no one could see through. For most of the early 1980s, cosmology felt settled. The universe expanded, galaxies rushed apart, and Hubble's law tied their speeds neatly to their distances. Astronomers had a picture they trusted, and the math behaved. The tools were getting sharper too. Photographic plates were giving way to CCD detectors. silicon chips that counted individual photons and turned faint smudges into precise measurements. Redshifts that once took whole nights could now be logged in a fraction of the time. That precision mattered because measuring a galaxy's distance had always been the weak link. Get the distance wrong, and you can't tell real motion from the ordinary stretch of expansion. New methods were closing that gap, linking a galaxy's brightness and rotation to how far away it truly sat. So the pieces were quietly falling into place. Better detectors, better distances, and a growing catalogue of galaxies waiting to be surveyed in bulk. The field was calm, confident, and almost bored. A team of 7 was about to point those tools at the strangest region of the sky. They came from 3 continents and eventually earned a nickname, the 7 Samurai, after a group of scientists who joined forces the way the film's warriors did. Alan Dressler, Sandra Faber, David Burstein, Roger Davies, Donald Lyndon Bell, Roberto Turlevich, and Gary Wegner. Their goal sounded almost simple: measure how fast a few hundred elliptical galaxies were actually moving through space. To do that, they needed real distances, not just redshifts. So they built a method around the internal motion of stars inside each galaxy, a relation that tied a galaxy's true size to how fast its stars swirled. Compare that to how big it looked, and you get a distance that doesn't depend on the expansion at all. With a distance in hand and a redshift measured, you can subtract the smooth Hubble flow and see what's left over. Any extra push or pull shows up as raw motion. They collected galaxy after galaxy, checked their numbers, and trusted the technique they'd spent years refining. Their careful survey handed back a number that made no sense. It wasn't just our galaxy drifting. When they plotted the motions across a wide patch of sky, hundreds of galaxies were moving in the same direction, all leaning toward one region far off in the constellation Centaurus. And they weren't drifting gently. This whole crowd was sliding along at roughly 600 kilometers per second, far faster than the expansion of the universe could account for. Something was adding hundreds of kilometers per second on top of the flow everyone expected. Picture a river you thought was still, and suddenly you notice the entire surface pulling one way. That's what the data showed. Galaxy after galaxy, spread across enormous distances, marching in step toward the same point. Groups this far apart shouldn't share a motion like that. Gravity works on what's nearby, yet these galaxies acted like they were all answering to the same distant call. The pattern was too coordinated to be noise, too large to ignore. They checked the region the stream pointed toward and found nothing bright enough to explain the pull. Whatever sat at the center of that stream, it was massive and it was hidden. So they gave it a name, the Great Attractor. It sat roughly 150 to 250 million light-years away in the direction of the Centaurus and Norma constellations, and it was reeling in everything around it, our galaxy included, at hundreds of kilometers per second. Naming a thing usually means you understand it. This was the opposite. The name was a placeholder for a gravitational hole in the data, a mass big enough to bend the motion of thousands of galaxies, with no clear object at the center to blame. And the strangest part is why it took so long to notice. This wasn't a faint smudge at the edge of the universe. It was close, cosmically speaking, close enough that it should have been one of the brightest concentrations of galaxies in our sky. But look toward Centaurus and Norma, and you don't see a crowd of galaxies. You see a dense band of stars, dust, and gas, glowing and blocking everything behind it. The reason we couldn't see it was our own galaxy standing in the way. Astronomers have a name for this problem. They call it the Zone of Avoidance, and it's not a small gap. The flat disk of the Milky Way, packed with stars and thick lanes of dust, wipes out roughly 20% of the entire sky. Point an optical telescope at that band and you're staring straight into our own galaxy's crowded plane. Visible light from anything behind it gets absorbed and scattered long before it reaches us. Whole regions of the distant universe simply go dark. And here's the cruel part. The pull we'd been chasing pointed almost exactly into that hidden strip. The one direction we most needed to study was the one direction we couldn't. So for years the maps just stopped there. A blank corridor cutting across the sky, right where the gravity was strongest. We knew something massive sat out that way, but we were reading its influence without ever seeing its face. Behind that curtain of dust, entire galaxy clusters were waiting undiscovered. That curtain's the zone of avoidance again, the same band where our own galaxy's disk crowds the view. Gas, dust, and packed stars pile up along the Milky Way's plane, and they don't just dim what's behind them, they swallow it. Optical light hits that wall and stops. Visible photons from distant galaxies scatter and get absorbed by interstellar dust long before they reach our telescopes. So the exact region tugging on us hardest was the one region our best instruments couldn't penetrate. And this isn't a thin sliver you can shrug off. The zone of avoidance blots out close to 20% of the entire sky. Roughly a fifth of everything out there sat behind a smear we couldn't read, and the source of that gravitational pull happened to be hiding right in the thick of it. Picture surveying a whole planet with a permanent blindfold across one stretch of the horizon. You can map everywhere else in detail, but the thing you most want to find keeps slipping into the gap. Every optical map had the same hole in the same place. To see through it, they'd have to abandon visible light entirely. So they switched wavelengths. Visible light gets swallowed by the dust and stars of our own galaxy, but other kinds of radiation don't care about that fog. X-rays slip right through it. Hot gas, trapped between galaxies, glows in X-rays, and hot gas is exactly what pools inside big galaxy clusters. Radio telescopes offered a second door. Hydrogen gas, the raw material galaxies are built from, hums at a wavelength of 21 centimeters, and that signal sails through the clutter untouched. Point a radio dish at the blocked region, and galaxies that were invisible in every photograph suddenly announce themselves by their gas. Infrared did the rest. Dust blocks the light you can see, but it glows in the infrared, and longer wavelengths pass through it far more easily than optical light does. Surveys like these let astronomers finally stare straight into the band of sky that had defeated every earlier map. One by one, the instruments started peeling back the curtain, and almost immediately, the effort paid off. The first thing those new eyes found was a cluster no one knew existed. They called it Norma, after the faint constellation it sits behind, and it landed almost dead center in the direction everything seemed to be falling. This wasn't a loose scatter of galaxies. It was a proper cluster, hundreds of them, packed tight, roughly 220 million light-years away, hiding in the one slice of sky we'd struggled to see through for decades. For a moment, it looked like the answer was just sitting there, a big, gravitationally bound knot, right where the models said the mass should be. If you'd been guessing where the pull came from, you couldn't have drawn a better bullseye. So astronomers did the obvious thing. They started adding up what Norma actually weighed, counting its galaxies, measuring how fast they orbited, estimating the mass holding them together. And that's where the confidence started to crack. The numbers came back too small. A cluster that size tugs on its neighbors, sure, but not on a region stretching hundreds of millions of light-years across. Norma alone couldn't explain the force we were feeling. So the search widened. Astronomers tallied every galaxy they could see near the attractor, the bright spirals, the fuzzy ellipticals, the whole crowded field around Norma. They added up the starlight and converted it into mass, the way you'd weigh a city by counting its lit windows at night. The sum kept coming up short. Even packing in the biggest galaxies at the center, the visible material topped out at maybe a tenth of what the pull demanded. You could stack every glowing thing in that direction and still be missing most of the weight. That gap is uncomfortable. Gravity doesn't round up or make exceptions, so if the motion was real, the mass had to be real too, sitting somewhere the telescopes weren't showing us. The light we could measure just wasn't heavy enough to steer a whole neighborhood of galaxies. And that left one option nobody liked saying out loud. The missing gravity had to come from something we still couldn't count. The stuff we can see, stars, gas, glowing clouds, adds up to barely a fifth of the matter out there. The rest gives off no light at all. It doesn't shine, doesn't reflect, doesn't block a single photon. We only know it's there because galaxies move like something heavy is holding them. Spin a galaxy and its edges should whip slower than its core, the way outer planets crawl compared to Mercury. They don't. The outskirts race just as fast as the center, as if a hidden mass were wrapped around the whole thing, roughly 5 times heavier than everything we can see. So the search widened. If ordinary light couldn't steer this neighborhood, then dark matter had to be doing the pulling, piled up somewhere out past our view. It became the invisible weight on the ledger, the entry that finally made the sums almost balance. Almost. Count every dark halo, add every hidden ton toward that direction, and the arrow still pointed at something bigger. Even dark matter's accounting left a gap this pull couldn't close. So the astronomers did the obvious thing. They started counting. If a mass this large sits toward Centaurus, its galaxies should be right there in the images, thousands of them clustered where the pull points. Teams swept that patch of sky with redshift surveys, logging each galaxy's distance one spectrum at a time. Every confirmed member added mass to the tally, another few billion suns pinned to the map. The catalog grew from hundreds into the thousands, and the region started to look genuinely crowded. On paper, the case looked solid, a concentration of galaxies sitting exactly where the Milky Way was being tugged, dense enough to explain a serious fraction of the motion. For a while, the count seemed to be catching up to the pull. But the deeper the surveys reached, the stranger the arithmetic got. Add another cluster, and the balance didn't settle. It shifted farther out. The more they counted, the more the numbers pointed somewhere beyond the attractor itself. So a strange thought crept in. What if the Great Attractor wasn't really the thing doing the pulling? What if it was just the closest bright spot in a much larger picture, the near edge of something we couldn't fully see? The math kept nudging that way. When astronomers tallied the mass of the attractor region, roughly a few times 1016 solar masses, it looked huge, but it still fell short of explaining how hard our whole neighborhood was being dragged at hundreds of kilometers per second. A big pull needs a big cause. And when the visible cause comes up light, the honest move isn't to fudge the numbers, it's to ask what you're missing and where it might be hiding. The attractor sat in a crowded stretch of sky, layered with clusters stacked one behind another along the same line of sight. Something that size and that far away could easily crouch in the glare of a nearer object, unnoticed for years. The real engine might be sitting far behind it. So the astronomers pushed their measurements outward, past the distance where the attractor was supposed to hold court. They tracked galaxies twice as far away, then farther still, watching for the moment the motion would settle and go quiet. If the attractor were the whole story, the flow should have slowed as they crossed it, the way a river slackens once it spills into a lake. It didn't slow. Galaxies well beyond the attractor were still drifting in the same direction, at speeds the local mass had no business producing. The pull wasn't fading with distance the way gravity from a single object should. It kept going, steady and cold, as if the attractor were just a way station on a much longer road. That was the part that unsettled people. You expect an anchor to hold you. Instead, the anchor itself seemed to be sliding, caught in the same current as everything around it. Whatever they thought they'd found, the numbers kept pointing through it, past it, into the dark beyond. The stream ran on toward something enormous and much farther away. The astronomers reached for the obvious move. They counted the mass they could see near the flow's direction and asked whether it was enough to explain the pull. It wasn't close. Every time they pushed their surveys deeper, the required mass crept upward. Add the galaxies at 100 million light-years, and the sum grew. Add the ones sitting twice as far out, and it grew again. The gap refused to close. Instead of settling on a number, the tally kept demanding more matter, always farther out than the last count reached. The center of gravity for our whole neighborhood sat somewhere they hadn't fully mapped yet. That pattern told them something uncomfortable. The thing steering these galaxies wasn't a modest clump nearby. It was heavier, and it was deeper, hiding at a distance their early catalogs barely touched. As their maps stretched out toward that direction, the same feature kept reappearing in the data: larger with every look. On the horizon of the data sat a supercluster of staggering scale. Push out about 650 million light-years, roughly 4 times farther than the Great Attractor, and you hit it. Astronomers call it the Shapley supercluster, after Harlow Shapley, who first noticed an odd clot of galaxies in that patch of sky back in the 1930s. He had no idea what he was looking at. This is the densest pileup of galaxies anywhere in the nearby universe. We're talking dozens of galaxy clusters, each one already a swarm of hundreds or thousands of galaxies, all packed into a single region. Bundle it up and you get the mass of more than 10,000 Milky Ways, maybe far more. And it sits almost dead in line with the direction our galaxy is being pulled. That's the part that made people sit up. The Great Attractor was closer and easier to see, but behind it, much larger, loomed this second thing, tugging along the very same line. So the picture got complicated. 2 masses, one nearer and one far heavier, both pulling from roughly the same corner of the sky. The question became how much of our motion Shapley alone was driving. So astronomers set up a kind of accounting problem. On one side, the Great Attractor, closer to us at about 250 million light-years, close enough that its gravity should tug hard. On the other, the Shapley Concentration, roughly 650 million light-years out, but packing far more mass into a single crowded region. The two sit in nearly the same direction, which makes them maddening to separate. Pull comes from that corner of the sky, but which one deserves the credit? Distance weakens gravity fast, so a nearer, lighter clump can rival a distant, heavier one. The numbers refuse to sort themselves cleanly. Some of our motion clearly answered to the Great Attractor. Some of it seemed to reach past that, drawn toward Shapley sitting behind it. It started to look less like one culprit and more like a contest, 2 heavyweights leaning on the same rope, each claiming a share of the drift. And when researchers added their combined pull and checked it against how fast we're actually traveling, the totals still didn't quite settle. Even together, they might not account for everything moving us. So put a number on it. The Great Attractor, sitting about 150 million light-years out, tugs hard, but its neighborhood just doesn't hold enough mass to explain the full drift on its own. Add in Shapley, further off and heavier, and the ledger looks better. Better isn't closed. Depending on which survey you trusted and how deep it reached, the known concentrations accounted for somewhere around half to 2/3 of our motion. That's a real chunk. It's also a gap you can't wave away. Because the velocity itself was measured, roughly 600 kilometers per second of steady drift, and you don't get to negotiate with a measurement. You add up every mass you can see, you sum the pull, and you compare. When the two sides refuse to match, one of them is hiding something. The tempting move was to keep piling on structure until the books balanced. But every honest count kept coming up short, and the shortfall didn't shrink towards 0. A stubborn remainder still pointed at empty sky. So astronomers went back to the sky map and traced the leftover motion carefully. When they lined up our galaxy's velocity with the structures around us, part of the vector landed on the Great Attractor, but a real chunk of it aimed somewhere else, off toward a patch of sky that held almost nothing at all. Not fewer galaxies, not a thinner cluster, a stretch of space that came back nearly blank on every survey they pointed at it. And yet our motion leaned in that direction, as if something out there had a claim on us. That's the kind of result that makes you check your instruments twice. A pull is supposed to come from mass, from something you can count and weigh. But this signal traced back to a hole in the map, a direction with no obvious source to explain the tug. Every framework we had assumed gravity flows one way, that galaxies drift toward whatever's heavy and crowded. An empty region shouldn't do anything, unless we'd been reading the whole picture wrong. What if we weren't only being pulled, but also pushed? Think about how gravity is supposed to work. Mass pulls. More mass, more pull, and empty space just sits there doing nothing. So the idea that a region with almost nothing in it could shove galaxies away sounds like it breaks the rules. But it doesn't, not really. In a universe filling with matter, an underdense patch has less than its share. Everything around it has more, so relative to that surrounding density, the void behaves like a hill instead of a valley, and galaxies drift down and away from it. That reframes the whole problem. Maybe our motion wasn't one giant hand reaching out to grab us. Maybe part of it was a wide emptiness at our backs, quietly nudging us forward while something else tugged from ahead. It's an uncomfortable thought, because it means the culprit might be a place with nothing to see. You can't photograph an absence. You can only infer it from how everything nearby moves. To test it, cosmologists needed a three-dimensional map of cosmic flow. So they built one, not from pictures, but from velocities. For thousands of galaxies, they measured how fast each was moving and in what direction, then subtracted the steady stretch of cosmic expansion. What's left over is the raw motion, the part that expansion alone can't explain. Feed those leftover velocities into a computer, and something remarkable happens. The scattered dots stop being isolated points. Arrows appear at every galaxy, each one pointing where that galaxy is actually drifting once you strip the expansion away. Line up enough arrows and they stop looking random. They bend, they converge. Whole regions of the sky start moving together, the way water on a hillside finds the same channel. The math turns a field of dots into currents, and those currents flow. You can trace them by eye now. Streams of galaxies pouring in the same direction, merging into larger streams, all leaning towards some low point you can't see directly. The motion has a grain to it, a downhill sense, as if the whole neighborhood were tilted. When the map rendered, it showed something with edges, like a basin. Follow any single galaxy, and it barely tells you anything, but trace thousands at once, plot each velocity as a tiny arrow, and the arrows stop looking random. They line up. They bend toward each other, the way rain on a hillside finds the same gully, then the same creek, then the same river. That's what the flow maps showed. Whole sheets of galaxies sliding along parallel tracks, then curving inward as they neared a common seam. The streamlines from one side of the sky and streamlines from the far side weren't independent. They were feeding the same drain, tilting toward the same invisible floor. On Earth, that pattern has a name. Every drop that falls inside a watershed ends up in one river, and the ridge that separates one watershed from the next decides where the water goes. The galaxy flows behaved exactly like that, converging toward a single low point across hundreds of millions of light years. And once you see water flowing, you start asking where the high ground is, where one basin ends and another begins. Those streams traced a boundary no one had drawn before. So the team did what a hydrologist does with a mountain range. They followed each flow line back to its source, tracing the direction galaxies were drifting velocity by velocity. Where the lines pointed inward, toward a common floor, those galaxies belonged together. Where they peeled away toward a different low point, they belonged to something else. That's the trick that makes the whole thing work. You don't measure a wall or a rope. You watch which way things fall, and the dividing crest reveals itself. The ridge where a galaxy on one side tumbles toward us and a galaxy on the other slides away forever. Draw every one of those lines and a shape starts to close, a surface where the inward drift stops, where motion tips the other way. Inside it, everything is quietly falling toward the same distant floor, bound by the same slow current. They finally had an edge, a real border stitched from thousands of tiny motions, and when they stepped back to see what sat inside that border, the region it enclosed turned out to be almost unimaginably large. They gave it a name that fit the scale, Laniakea, Hawaiian for immeasurable heaven. It stretches across roughly 520 million light-years, and inside its border sit about 100,000 galaxies, the Milky Way among them. This wasn't a cluster you could point to. It was a shape defined entirely by motion. The definition itself was the leap. Instead of drawing lines around bright clumps of light, the team traced where every galaxy was drifting, then asked which ones were falling inward together. Everything that shared the same downhill slide belonged to the same structure. Laniakea is the full watershed, the entire region whose galaxies pour toward one low point. So for the first time, we had a real home address, a supercluster stitched from thousands of quiet velocities rather than guesses about brightness. Our galaxy sits far out near one edge, sliding slowly toward the center, like water finding the bottom of a bowl. But knowing the shape of the basin raised a harder question about what carved it, because the Great Attractor was just the valley floor of this basin, not the cause. For decades, the Great Attractor sounded like a thing, some massive object crouched behind the galaxy, reeling us in by sheer weight. But once you map the whole flow, that picture falls apart. What we call the Great Attractor is really a location, the low point where dozens of galaxy streams happen to converge. It's the drain, not the hand on the drain. Nothing sits there pulling with special force. The valley is deep because that's the direction everything nearby is already sliding. And that reframing doesn't settle anything. It makes the ground feel less solid. If the bottom of the bowl is just where matter piles up, then the shape of the bowl itself needs explaining. Something tilted this whole region, set the slope, decided which way the rivers run. Laniakea isn't sitting still, cradling us at rest. The entire basin is drifting, leaning towards something farther out than the valley floor we thought we'd found. So what pulls Laniakea toward its own distant edge? Follow the drift outward, and it keeps going past the ridgeline we just drew. Laniakea's whole flow leans toward a spot roughly 650 million light-years away, well beyond the border we called our own. And sitting right there, in that direction, is a concentration of galaxies too big to ignore. It's the Shapley Concentration, the densest collection of galaxy clusters in our part of the universe. Hundreds of clusters, packed into one region, all of that gravity pulling in the same direction our supercluster is already sliding. On a flow map, the streamlines don't stop at Laniakea's edge. They bend toward Shapley, like water, tilting downhill. So maybe that's the answer. A giant mass out past the boundary, tugging everything, including us, toward it. But when astronomers measured how hard we're actually being pulled, Shapley's gravity only covered part of the budget. Something on the far side of the sky wasn't adding up. Directly opposite Shapley, the sky was strangely, meaningfully empty. Point a telescope at that empty patch, and you find almost nothing for hundreds of millions of light-years. No bright clusters, no crowded threads of galaxies, just a vast hollow where the cosmic web thins out to almost nothing. Astronomers started calling regions like this voids, and this one sits directly behind the direction we're falling toward. Here's what makes it unsettling. A void isn't just scenery. In a universe where matter tugs on matter, a patch with far less matter than average pulls back on you far less than everything around it. So you drift away from the emptiness, sliding toward the crowded side, almost as if the whole were pushing you off. That means the deficit on one side and the pile-up on the other are two halves of the same motion. We're not only being drawn toward what's dense, we're being nudged away from what's barren, and both effects point us the same way. Emptiness, it turned out, can shove as hard as mass can pull. In 2017, a team led by Yehuda Hoffman gave that empty region a name. They called it the dipole repeller, a vast underdensity sitting almost directly opposite the Shapley concentration in our sky. Picture the map. On one side, a crowd of galaxies clustered thick with mass. On the far side, a hollow where almost nothing lives. The Milky Way sits between them, and both are working on us at once. The dense side tugs, the way gravity always tugs toward more stuff. The hollow side does something stranger. Everywhere around that void, matter is being pulled elsewhere, so relative to it we drift outward, as if the emptiness itself were pressing against our backs. Two influences, roughly 600 million light-years apart, aimed in nearly the same direction. One a mountain of galaxies, the other a canyon of nothing. When Hoffman's group ran the numbers on both together, the picture sharpened. Push and pull together finally began to add up to the speed we measured. Think of it as two hands on the same wheel. Shapley reaches out from beyond, roughly 650 million light-years off, and tugs everything in our neighborhood toward its dense heart. Meanwhile, the empty region behind us gives a shove, because there's less matter back there to hold us in place. Neither force acts alone. The attraction pulls us forward, the emptiness nudges from behind, and both point our little corner of space in nearly the same direction. Line up the arrows, and they don't cancel, they stack. That combination is what closed most of the gap. For decades, the numbers came up short, one culprit never quite explaining our full motion. Add the push to the pull, and suddenly, the budget looked close to balanced. Hundreds of kilometers per second, sorted into contributors we could actually point at on a map. Close, though, isn't the same as solved. A slice of the motion still sat unaccounted for, tucked away where the cleaner story preferred not to look. But one older, stranger claim still haunted the field. Back in 2008, a team led by Alexander Kashlinsky went looking for motion in the faint glow left over from the Big Bang. They studied more than 700 galaxy clusters, measuring tiny temperature shifts in the cosmic microwave background as those clusters swept across it. What they reported wasn't subtle. The clusters seemed to be sliding in the same direction, all of them at close to 1,000 kilometers per second. Not scattered, not random, a single coordinated drift stretching across billions of light-years of space, pointed toward one corner of the sky near Centaurus. That was the unsettling part. The attractors we'd catalogued, the walls and the giants, could explain the nearby pull. They couldn't explain a current this vast, this uniform, running past the edge of everything we'd mapped. So Kashlinsky gave it a name that carried its own weight: dark flow. Something was tugging on these clusters from a direction our telescopes had never resolved. If real, it hinted at structures outside everything we can ever see. To understand why that idea unsettled people, you have to look at where our seeing actually stops. Light travels fast, but the universe is old, and there's a hard edge to how far any signal has had time to reach us. That boundary sits around 46 billion light-years in every direction, the horizon of everything we can ever observe. Beyond it, space almost certainly keeps going, but whatever's out there has never sent us a single photon, and it never will. The expansion carries those regions away faster than their light can close the gap. So when dark flow pointed toward a pull coming from past that horizon, it was pointing at territory physics said we could never check, a tug from the unseeable. Structures we could feel but never confirm, casting their influence across a line we can't cross. That's a claim that makes careful scientists deeply uncomfortable. An effect with no visible cause, sourced from beyond the edge of sight. The measurements behind dark flow were about to be torn apart. The core of the fight came down to the signal itself. Kashlinsky's team measured tiny temperature shifts in the cosmic microwave background, then used distant galaxy clusters to extract a bulk motion of roughly 600 to 1,000 kilometers per second, all pointed in one direction. If that held up, whole swaths of the universe were drifting towards something outside our horizon. Critics went straight for the method. They argued the effect sat buried inside the noise, that the error bars were wide enough to swallow the whole result. Rerun the analysis with slightly different assumptions, they said, and the flow shrank toward zero. Then the Planck satellite weighed in. Its team ran their own search across the same cosmic background and reported no significant bulk flow at all. Kashlinsky pushed back, saying Planck's pipeline had scrubbed away the very signal they were hunting for. So you had two camps staring at the same sky and reading it in opposite ways. One saw a river, one saw static. Newer data would either bury the idea or blow it wide open. So the instruments got sharper. The WMAP satellite, launched in 2001 and later Planck in 2009, mapped the cosmic microwave background with a precision that made earlier measurements look like sketches. That faint glow, cooled to just 2.7 degrees above absolute zero, carries a tiny lopsidedness, one side slightly warmer than the other. That warm spot is the dipole, and it tells us the Milky Way is moving at roughly 630 kilometers per second relative to the radiation left over from the Big Bang. The question was whether the Great Attractor could account for all of it. Better galaxy surveys stacked distances and velocities across a wider slice of sky, trying to add up every pull acting on us. When they ran the numbers, the tug from that one region explained a big chunk of the motion. But not the whole thing. Something farther out, something the early maps couldn't reach, still seemed to be adding its own faint drag. The verdict trimmed the mystery, but didn't kill it entirely. So sought the wreckage. The Great Attractor was real, that held. A genuine overdensity near the constellation Norma, roughly 150 million light-years out, tugging on everything around it. But its pull, once credited with our full 600 kilometers per second drift, kept shrinking as the measurements sharpened. Other pieces didn't age as well. Early claims of a single tidy source, one clean bullseye behind the galactic plane, dissolved once astronomers looked past it. The signal wasn't fake, but it wasn't the whole story either. Something bigger sat in the same direction, farther and heavier, and the attractor was starting to look like a foreground feature in front of it. What passed the test was simple and stubborn. We're moving. The direction is fixed, and the speed is too high to explain with anything close by. That last fact refused to fade. Every trimmed estimate, every corrected map left a residual motion that local mass just couldn't account for. And that leftover, small as it looked, was the loose thread. What survived pointed back at the biggest theory of all. That theory has a name that sounds almost bureaucratic. Lambda CDM. The lambda stands for dark energy, the thing pushing space apart faster and faster. CDM is cold dark matter, the invisible scaffolding that holds galaxies together. Put them side by side, and you get the ruling picture of the universe. Roughly 68% dark energy, about 27% dark matter, and a thin 5% of ordinary stuff, the atoms in stars, planets, and you. It fits the cosmic microwave background almost perfectly. It predicts how galaxies cluster over billions of light-years. For decades, it's passed test after test, so cleanly that most cosmologists treat it as settled ground. That's what makes the leftover motion so uncomfortable. A model this successful isn't supposed to have loose threads dangling off it. But there we were, drifting through space at hundreds of kilometers a second, in a direction the smooth, tidy math didn't fully explain. A few small galaxies, tugging on a number the whole framework depended on. Our motion was quietly stress-testing that entire model. So teams went looking, and the numbers came back stranger than anyone wanted. When you measure how whole swaths of galaxies drift together, a bulk flow, the standard model gives you a ceiling. On the largest scales, everything should slow toward the same average, roughly 200 kilometers a second, and falling as you zoom out. Instead, some surveys clocked bulk flows near 400 kilometers a second, and they weren't dropping the way they should. A few pushed the measured motion out across hundreds of millions of light-years and still saw galaxies marching in step. That's not a gentle drift. That's a coordinated push the math didn't order. Now, measuring motion at those distances is brutal, and the error bars are wide enough to argue about. Maybe it's noise. Maybe it's a systematic quirk in how distances get pinned down. But the signal kept showing up in different datasets, from different groups, pointing roughly the same way. And that's the part that gnaws at you. A little extra speed is a puzzle you fix later. Too much speed, over too large a volume, means the framework itself is leaking somewhere. If the flow really is too fast, something fundamental is wrong. By the early 2000s, multiple teams were mapping peculiar velocities across wider patches of sky. The numbers started disagreeing with each other in small but stubborn ways. One survey would measure a galaxy moving 150 kilometers per second faster than the model predicted. Another would find a neighboring cluster drifting 200 kilometers per second slower. The mismatches weren't random noise. They clustered in specific directions, as if entire regions of space were moving coherently in ways the mass distribution couldn't explain. Some galaxies seemed pulled harder than their neighbors, even when sitting in nearly identical environments. Two possibilities loomed. Either the surveys were flawed, riddled with calibration errors or selection bias, or the predictions were wrong because the underlying model of how structure grew in the universe was incomplete. Both options were uncomfortable. One meant wasting years chasing phantom signals. The other meant rewriting textbooks. The data sat in spreadsheets, unresolved. Astronomers couldn't yet tell if these were mistakes or breakthroughs. So which was it? A slip in the measurements or a signal the universe was trying to send? For years, that question hung over the numbers, like a fault line nobody wanted to stand on. The case for error was easy to make. Distances that far out lean on chains of assumptions, each rung adding its own uncertainty. A miscalibrated brightness here, a bad guess about dust there, and a whole flow of galaxies could turn into a ghost. But the discrepancy kept showing up. Different teams, different instruments, different corners of the sky, and the anomaly refused to average away. That stubbornness is what made people nervous. Random errors cancel. This one didn't. If it was real, the tidy picture of a smooth, evenly stretching cosmos had a crack running straight through it. And a crack like that doesn't stay small. It spreads into everything built on top of it. For now, the two possibilities sat side by side, neither one winning. Settling it would take a survey more precise than any before. So teams set out to weigh the whole neighborhood, not just the Milky Way, but Laniakea itself, the giant basin our galaxy sits inside, along with every cluster crowded near it. To do that, you count the galaxies you can see, then add up the mass of their stars, their gas, and the dark matter wrapping around each one. It sounds simple, it isn't. A galaxy's light is easy to catch, but light is the smallest part of the bill. Most of the weight hides in halos you can't photograph, so astronomers infer it from how fast things orbit and how strongly clusters bend the light passing behind them. They ran the numbers across huge volumes, region by region, cluster by cluster, building a ledger of everything within reach. Every galaxy counted, every stream of gas measured, every halo estimated and stacked onto the total. The goal was a single figure for how much matter our corner of the universe actually holds. And when the tally came back, it didn't match the picture in the sky. The weigh-in revealed our home was lighter than it looked. So if the matter came up short, where did the missing weight go? The simplest answer is that it was never there to begin with. Our neighborhood might sit inside a stretch of space that's genuinely emptier than average, a low-density pocket scooped out of the cosmic average. Astronomers have a name for a region like that. It's called a void, and they're not rare. The universe is threaded with them, vast bubbles where galaxies thin out, and the space between them yawns wider than anywhere else. Counts of nearby galaxies started pointing the same direction. Out to something like 300 million light-years, the number of galaxies per volume runs noticeably below the cosmic mean, by roughly 15 to 20% in some measurements. Not empty, just lighter. And that changes the math in a quiet, sneaky way. When you're sitting inside a hollow, the stuff outside pulls at you unevenly, and the space around you behaves a little differently than the textbook average would predict. Living inside a void could explain puzzles we'd blamed on the attractor. So how empty are we talking? In the late 2000s, astronomers mapping galaxy counts around us noticed something off. The region surrounding the Milky Way holds far fewer galaxies than an average patch of the universe should. We're not near the crowd, we're near a hole. They gave it a name, the local void, and it's staggering. Estimates put it at 150 to 300 million light-years across, a stretch of space where galaxies thin out to a whisper. Its edge sits uncomfortably close to us, just past the far side of our own neighborhood, and the Milky Way appears to be riding along that boundary. Here's why that unsettles people who measure the sky. Matter on the crowded side keeps tugging, while the empty side tugs back with almost nothing. So we get shoved away from the void at hundreds of kilometers per second, a push that mimics a pull. Some of the motion we credited to distant giants might just be us fleeing an absence. And an absence is hard to weigh. You can't point a telescope at nothing and read a mass off it. That bubble might be nudging every number we trust. Here's the trouble with measuring expansion from inside a moving neighborhood. If your whole region is drifting one way, The galaxies ahead of you look like they're receding faster, and the ones behind look slower. You're clocking speeds from a platform that's already sliding. Now, add that emptiness around us. Sitting near the edge of an underdense patch, matter thins out on one side, so gravity tugs us gently outward toward the denser walls. That local pull mixes into every velocity we record, and it doesn't cancel cleanly. So when astronomers measure how fast nearby galaxies rush away, part of that number isn't cosmic expansion at all. It's our own peculiar motion, our slide toward the crowded regions, leaking into the reading. Untangling the two takes careful surveys and a lot of assumptions about what surrounds us. Get the local map wrong, and the expansion rate you calculate comes out biased, tilted by where you happen to stand. A few percent off might sound harmless. It isn't. This distortion collided with the biggest argument in modern astronomy. There are two ways to clock how fast the universe is expanding, and they should agree. One reads the early universe, the faint glow left over from 380,000 years after the Big Bang, and works forward to predict the expansion rate today. That number lands near 67 kilometers per second per megaparsec. The other method skips the deep past entirely. It measures nearby galaxies directly, using pulsing stars and exploding stars as distance markers, then watches how fast they recede. That path keeps landing near 73. 6 units apart, both camps have spent decades tightening their instruments, hunting for the mistake that would close the gap. The gap refuses to close. As the error bars shrink, the two answers drift further from any chance of being the same measurement. If both are right, something in our picture of the cosmos is broken, and the local method leans hard on how galaxies move right around us, the very motions we've been tracking this whole time. Our own motion may be quietly tipping the scales in that fight. There are two ways to measure how fast the universe is expanding, and they refuse to agree. One starts in the infant cosmos, reading the faint glow left over from 380,000 years after the Big Bang and running the physics forward. It arrives at an expansion rate near 67 kilometers per second for every megaparsec of distance. The other method stays close to home. It climbs a ladder of nearby distances, star by star, galaxy by galaxy, and lands closer to 73. That gap sounds small, but it's held firm through years of sharper data and tighter error bars, and it hasn't shrunk the way a simple mistake should. The local number depends on clocking galaxies in our own neighborhood, then subtracting the tug our region adds to their motion. Get that subtraction wrong, and the whole ladder tilts. So researchers went back and carefully stripped out the pull steering our patch of sky, the flows we've been chasing all along. You'd expect that cleanup to calm things down. It didn't. Correcting for our flow only made the disagreement more interesting. So look at what we're holding now. Our galaxy drifts at about 600 kilometers per second towards something we can't cleanly see. Whole regions of sky show galaxies streaming together, sliding the same direction as if pulled by a hand we haven't located. Then there's the number that won't sit still. Measure the universe's expansion using the early cosmos, and you get roughly 67 kilometers per second per megaparsec. Measure it using nearby galaxies, and you get closer to 73. Both sides swear their rulers are right. For a while, these looked like separate puzzles, a flow problem here, an expansion problem there, a map with a shadow across it. But they keep brushing up against each other in ways that feel less like coincidence. Because every one of them leans on the same shaky footing. To measure our motion, we assume we know the still background. To measure expansion, we assume our neighborhood is ordinary, not sitting somewhere strange. Underneath every thread lay one question about how much we can trust our own view. Every astronomer works from one platform. We sit inside the Milky Way, orbiting a star 2/3 out from the center, carried by a galaxy that's already moving. The light we collect has crossed space while we drifted through it. When we measure a distant galaxy's velocity, we're really measuring the difference between its motion and ours. Subtract our speed wrong, and every conclusion downstream changes. The cosmic microwave background gives us one anchor, but it's a single reference frame painted across the whole sky. To check our work, We need independent measurements from angles we can't occupy. We need distances and velocities for thousands of galaxies, mapped with enough precision to see whether the flows we calculate actually converge on the structures we think are pulling them. For decades, the data was too sparse, the distances too uncertain. Catalogs listed a few hundred galaxies with reliable measurements. Gaps in coverage left entire regions blank. A new generation of surveys was built to escape that single point of view. That effort took shape as Cosmic Flows, a project led by Brent Tully and his collaborators to catalog not just where galaxies sit, but how fast and which way they're moving. Instead of a few hundred distances, they stitched together tens of thousands, each one a tiny arrow pointing through space. The trick was measuring real distances independently of redshift, using the brightness and rotation of galaxies as standard rulers. Subtract the tidy outward flow of expansion, and what's left is the peculiar velocity, the part driven by gravity alone. Every galaxy's motion became a data point in a much larger current. By the third and fourth releases, the maps stretched hundreds of millions of light-years in every direction, filling in regions that older catalogs left dark. For the first time, you could watch matter drifting in coordinated streams across enormous volumes, like reading the wind from scattered leaves. And when they turned those arrows into a full picture of our own patch of the universe, the result stopped being a chart of distant strangers. Its reconstruction of our neighborhood was about to get personal. Here's what happens when you follow those arrows out past Laniakea's edge. The velocities don't simply stop at the border astronomers had drawn. They keep leaning, ever so slightly, toward one distant region far beyond our own basin, as if our entire supercluster were itself being nudged. Laniakea spans about 500 million light-years and holds roughly 100,000 galaxies, which sounds like a complete world. But a basin is defined by where its flows converge, and the flows near our outer edge don't fully settle. Some of them tip outward, toward a mass concentration so distant that Laniakea starts to look less like a destination and more like a way station. When you zoom out on the flow maps, our supercluster stops looking like an island. It looks like a bay, a big, quiet bay opening onto something even wider, with currents that pass right through us and carry on toward a deeper pull we can barely see. What looked like our whole home might be one lobe of something greater. Here's the trouble with drawing a line around a place you've never seen the edge of. Laniakea was mapped from the velocities we could measure, roughly 8,000 galaxies moving in the local neighborhood. Push the survey deeper, out past where our instruments start to blur, and those clean edges start to soften. When you add more distant galaxies to the flow map, the borders shift. A supercluster that looked separate suddenly shares a current with ours. The valley that seemed to fence us in turns out to spill over into the next one, and the flow keeps going. Some models suggest what we call Laniakea might just be a shallow dip inside a far larger basin, one that swallows several superclusters at once. Under that view, our 500 million light-year home isn't the container. It's a room in a much bigger house we haven't finished measuring. And that changes what a boundary even means out here. If a deeper map keeps merging basin into basin, then every wall we've drawn is really just the limit of how far we could see when we drew it. The boundary that defined us might not be a boundary at all. So here's the uncomfortable part. When we call Laniakea our home supercluster, we're borrowing a word that implies belonging, something held together. But being drawn toward the same low point isn't the same as being bound to it. A galaxy can drift toward the valley floor for billions of years and still never arrive. Space itself is stretching underneath that motion, widening the very distances the flow is trying to close. Two galaxies falling the same direction can still end up farther apart than they started. That's the quiet horror of it. Laniakea might not be a structure at all, just a snapshot of everything that happened to be leaning the same way when we looked. Give it enough time, and those 100,000 galaxies could scatter, the currents thinning out until nothing links them but a shared memory of direction. Whether our home survives as one thing or comes apart at the seams comes down to a contest we haven't measured yet. On one side, gravity, pulling everything toward the floor. On the other, something pushing back. Dark energy was about to decide our home's ultimate fate. In 1998, two teams measuring distant supernovae found something nobody expected. The universe wasn't just expanding, it was accelerating. Some invisible pressure, later named dark energy, was overpowering gravity on the largest scales. At first it seemed like an abstract problem for cosmologists, but dark energy doesn't wait for permission. It drives space apart faster than gravity can pull matter together. Galaxy clusters that were once headed toward collision now drift away from each other, their futures rewritten. The Great Attractor pulls us at 600 kilometers per second. Shapley pulls even harder. But dark energy isn't competing in the same arena. It doesn't pull or push individual objects. It stretches the fabric itself, and over billions of years, that stretch wins. Our local group will stay bound. Andromeda will collide with us. But the superclusters we're streaming toward, they're being carried away on an expanding tide we can't overcome. It meant we might never actually arrive where we're headed. Keep that in mind. So picture the Milky Way as a swimmer, stroking hard toward a distant shore. Every second we close a little more distance, roughly 600 kilometers with each tick of the clock. That sounds relentless, and for the nearby crowd of galaxies bound to us by gravity, it is. But the shore itself is drifting. Space between us and the Great Attractor keeps stretching, and the farther out you look, the faster that stretching adds up. Our motion is real, yet it's fighting a current that never tires and never slows. For the galaxies packed tight in our own neighborhood, gravity wins the local battle. Step back to the scale of hundreds of millions of light years, though, and the math flips. Expansion is opening ground faster than any infill can close it. So the pull is genuine, the direction is set, and still the gap refuses to shrink to zero. We're headed somewhere with everything we've got, and the ground keeps sliding out from under the trip. The destination we've chased this whole time may be one we can never touch. The pursuit feels real enough. Every velocity measurement confirms it. The local group slides at 631 kilometers per second toward the Great Attractor's coordinates, and for decades, astronomers treated that like a compass bearing toward a place we'd eventually cross. But space expands between us and the target faster than gravity can reel us in. The attractor sits 220 million light-years out, embedded in expansion's flow. Close that gap at our current speed, and you'd need 350 million years, except the gap itself grows by 15,000 kilometers every second. You're swimming upstream in a river that accelerates. The shore looks fixed, the effort is genuine, but the finish line recedes. Not because the pull weakened, because the track lengthens under your feet faster than you move. It's a race rigged by geometry. Gravity tugs us forward through local space, while expansion stretches the space itself. Both forces operate at once. Neither illusion, neither wrong. The mirage isn't the destination. It's the assumption we'd arrive. Reconciling pull and expansion required rethinking what motion even means out here. When a galaxy moves, two things happen at once. Space itself stretches, carrying everything with it like dots on an inflating balloon. But galaxies also drift through that expanding fabric, pushed or pulled by gravity. The first is Hubble flow. It's smooth, predictable, tied to the expansion rate of the universe. The second is peculiar velocity. It's local, messy, driven by every nearby mass tugging or shoving. You can't measure them separately. When you clock a galaxy's speed, you get the sum. Teasing them apart means modeling the expansion, then subtracting it. What's left is the peculiar component, the motion that gravity alone commands. The Great Attractor and Shapley aren't fighting Hubble expansion. They're steering galaxies within it, bending paths that would otherwise follow the cosmic flow. That distinction is the key to what really steers our galaxy. So picture the Milky Way sitting in traffic, tugged in half a dozen directions at once. The local group holds us close, Andromeda reeling us in from just 2.5 million light-years away. That's the near stuff, the family pull we already know. Then the field widens. the Great Attractor leans on us from about 150 million light-years off, sitting in the direction of Norma and Centaurus. Behind it, farther still, the Shapley Concentration adds its own weight from roughly 650 million light-years, a pile-up of thousands of galaxies bending our path from deep in the background. And it isn't only pulling. There's a region emptier than average shoving us from the opposite side, a nudge from where the mass isn't. Add them together, and the Milky Way's true motion is the sum of every one of these, a single arrow stitched from many hands. Every one of these forces is real. Every one leaves a mark on our velocity. But when you finally weigh the whole tally, they don't split evenly. One influence, it turns out, outweighs all the rest. So which one wins? Line them all up. The Milky Way's pull inside the local group, Andromeda swinging toward us, the tug of the Virgo cluster hauling on our little neighborhood. Each contributes a piece of the 630 kilometers per second we clock against the cosmic background. But contributions aren't votes. A nearby object can nudge you hard, while a distant one, if it's massive enough, quietly steers the whole flow. So the trick isn't just counting who's closest. It's weighing mass against distance, then following the arrow that survives once everything else cancels out. For years, the obvious suspect sat right in the middle of the answer. The overdensity we'd spent decades naming, the one that gave this whole story its title, seemed like the natural champion. It's big, it's in roughly the right direction, and it had the headlines. But when the numbers finally came in, they pointed somewhere else. The winner wasn't the object we named the whole mystery after. So the honest thing to do was stop trusting any single object and start stacking the evidence. Not one survey, not one telescope, but layers of independent measurements that shouldn't agree unless something real was underneath them. The flow data came first. Thousands of galaxy velocities, corrected for expansion, all leaning the same way at speeds around 600 kilometers per second. That drift didn't wobble or scatter. It held steady across the whole southern sky. Then came the mass counts. Add up every visible galaxy in the pull direction, weigh the clusters, tally the dark matter their motions implied, and the ledger kept coming up short of what the speed demanded. And then the empty spaces. Map where the galaxies aren't, and those voids sit in a pattern that isn't random either. They line up on the opposite side, as if we're being nudged from behind as well as tugged from ahead. 3 separate lines of evidence, gathered by different teams using different instruments for different reasons. None of them was built to prove the others. Piece by piece, a single coherent story was clicking into place. So what did the story actually say? Our galaxy isn't drifting at random. It's caught between 2 forces working in opposite directions, and both leave a signature in the numbers. On one side, a dense concentration of mass tugs us inward, adding its gravity to the pull we'd been tracking for decades. On the other side, an unusually empty region behind us gives a shove, pushing us away from where there's almost nothing to hold on to. Pull from ahead, push from behind, both pointing the same way. That combination did something the earlier ideas couldn't. It explained the direction of our motion and got much closer to the full 600 kilometers per second we measure, without inventing anything new. And a good framework doesn't just fit the data you already have. It makes a prediction you can go out and check. If the push-pull picture was right, the flow of galaxies across a wide patch of sky should line up in a very specific way. One more observation would confirm whether the story truly held. So the astronomers built it. They took the measured motions of thousands of galaxies out to hundreds of millions of light-years and turned each one into a tiny arrow, showing not where a galaxy sits, but which way it's actually drifting through space. When those arrows were plotted together, the noise fell away and a pattern surfaced. Whole regions of the sky leaned the same direction, sliding toward the crowded zones near Norma and Centaurus, and away from the emptiest stretches. It matched the prediction almost line for line. The pull of dense clusters and the quiet shove from the voids weren't 2 competing guesses anymore. They were 2 halves of one flow, and the map showed them working together across the whole neighborhood. You could trace a current of galaxies streaming along, our own Milky Way riding in it, all bending toward the same distant basin. Nothing had to be assumed. The motion was just there, drawn out in front of us. And once you can see the current you belong to, you can see where it carries you. That map finally let us write down our true address in the universe. Start close to home. The Milky Way sits inside the local group, a small huddle of galaxies about 10 million light-years across, dominated by us and Andromeda, with a few dozen dwarfs tagging along. Zoom out, and that whole group is just one knot along a thread of the cosmic web. We're not floating free. We're stitched into a larger structure, riding a current of galaxies that all lean the same direction. Pull back further, and the local group turns out to sit near the far edge of Laniakea, a basin some 520 million light-years wide, holding roughly 100,000 galaxies that all drain toward a single low point in the flow. And the direction we're pulled? Toward the dense pileup out near Shapley, hundreds of millions of light-years off, the biggest concentration of mass anywhere in our neighborhood. So that's the address. Milky Way, local group, Laniakea, sliding toward Shapley. It's a real location in a real structure, mapped and measured. But knowing the address only sharpened the strangest fact of all. Laniakea spans 520 million light-years. The Great Attractor sits 150 million light-years away, hidden behind the galactic plane. Shapley is another 500 million light-years beyond that. Numbers at that scale stop meaning anything until you attach a speed. We're moving toward the Great Attractor at 600 kilometers per second. That's relative to the cosmic microwave background, the closest thing we have to a universal rest frame. 600 kilometers every single second. The Milky Way weighs around 1.5 trillion solar masses. Andromeda is similar. The local group combined, maybe 3 trillion. All of it drifting in one direction, pulled by something we can barely see and don't fully understand. But here's what makes astronomers pause when they talk about it. The motion isn't theoretical. It's not inferred from old data or a quirk of one telescope. Every measurement, every survey, every independent method confirms the same thing. State it plainly, and it changes how you see the night sky forever. 600 kilometers per second. That's the Milky Way's peculiar velocity, the part of our motion that isn't cosmic expansion. It's 1.3 million miles per hour, aimed at a patch of sky near Centaurus and Hydra. To put that in perspective, Earth orbits the Sun at 30 kilometers per second. The Sun circles the galactic center at 220 kilometers per second. But the entire galaxy, all 200 billion stars, and their dark matter halo, is being swept along at nearly 3 times that speed by something outside our local control. It means every second we've existed, we've traveled 600 kilometers closer to the structure pulling us in. Every breath, every heartbeat, every moment in human history has happened while we drift through space faster than any object we've ever built. The number itself is precise. The margin of error has shrunk decade by decade as instruments improved. What remains uncertain isn't the speed, but the question of what, exactly, commands that kind of authority over a galaxy. That speed is the fingerprint of everything we've been chasing. Think about what that number actually encodes. Every gram of mass within reach, every unseen filament of dark matter, every distant cluster tugging from hundreds of millions of light-years away, leaves its mark on how fast we move and where we're headed. Our velocity isn't random. It's the sum of every pull written into a single vector. That's why the measurement matters so much. If you can nail our exact speed and direction relative to the smooth background of the cosmos, you're holding a compressed record of the entire mass distribution around us. Nothing gets left out. The gravity of things we can't even see still bends into that one arrow. So the motion of the Milky Way becomes a kind of decoder. Get the direction right, get the magnitude right, and you can start working backward toward the structures responsible. Every stray degree, every mistaken 100 kilometers per second points you toward a different culprit. Read it correctly, and the whole invisible architecture snaps into focus. So here's what that motion actually encodes. On one side, we're being nudged away from a huge underdense region, an emptiness that pushes rather than pulls. On the other, we're leaning toward a distant concentration of mass, hundreds of millions of light-years off, gathering galaxies by the thousands. Neither force works alone. The void behind us and the giant ahead of us line up almost along the same axis, so their effects add together instead of canceling out. The push from behind and the pull from ahead point the Milky Way the same direction, and the flow we measure is the sum of both. Layer that onto the map of streaming galaxies, and our whole neighborhood turns out to be sliding down a slope, drifting across the vast basin those flow lines carved out. We're not sitting still in a random place. We're riding a current that both the empty direction and the crowded one help drive. Repelled by nothing, drawn towards something, all of it happening across a single connected structure larger than anything we'd pictured before. This is the moment the opening image finally makes sense. So here's the thing we started chasing. The Great Attractor was never the puppet master pulling our strings. It's a low point, the floor of a vast basin, and we're sliding down toward it the way water finds the bottom of a valley. Our real motion, that 600 kilometers per second drift the whole Milky Way rides, comes from two things working together. Behind the plane of our galaxy sits an immense pileup of mass, the beginning of a supercluster far bigger than the Great Attractor alone. That crowded region reels us in from one side. And on the opposite side, a stretch of near emptiness gives us nothing to hold us back, so it effectively shoves us forward. Pull from the mass, push from the void, both pointing the same way across one connected web of galaxies. That's the answer. The direction our sky has been leaning this entire time isn't a mystery force. It's the shape of the cosmos itself, and we're just following its slope. But even this answer leaves one enormous piece unaccounted for. Add up everything we can see and weigh. Laniakea's slope, the pull of the Shapley Concentration, the shove from the void behind us. Line those up against the Milky Way's measured motion, roughly 600 kilometers per second toward that patch of sky, and the arithmetic almost closes. Almost. But a slice of that speed refuses to sit still on the ledger. When researchers tally the gravity of every known attractor out to hundreds of millions of light-years, they can account for most of the drift, not all of it. A stubborn remainder is left over, small but real, and it doesn't cancel out no matter how carefully they recount. What's driving that last piece? Nobody can point to a structure and say, there, that's the cause. It might be a mapping error, mass hiding where we can't look. It might be something farther out, tugging from beyond the range our surveys reach. And that's the uncomfortable part. That leftover keeps a door open to physics we haven't written yet. So what fills a gap that mass alone can't close? When the numbers keep coming up short, physicists start eyeing the rules themselves. Maybe gravity behaves differently across hundreds of millions of light-years than it does in our neighborhood. That's not a wild leap. It's the same instinct that once turned a wobble in Mercury's orbit into a whole new theory of gravity. If the flow we measure is real, and the mass we can find is genuinely too little, then either the map is incomplete or the physics is. Some researchers wonder whether dark energy isn't perfectly smooth, whether it pushes a little harder in some directions than others. Others ask if the universe has a texture we've been treating as flat, a slight lopsidedness baked in from the start. Each idea reaches for the same leftover motion, that stubborn drift no catalogue of galaxies fully accounts for. None of them is proven. All of them would rewrite pieces of the story we thought was settled. A few bold ideas are competing to fill that gap. Start with the simplest idea. Maybe there's just more structure out there than we've mapped. Bigger concentrations of mass hiding past the edge of our best surveys, still tugging in the same direction we already feel. If that's true, then the flows we measure aren't strange at all. We just haven't counted far enough. The second contender says the problem isn't what we can see, it's what we can't. Extra dark matter, distributed in ways our models don't predict, could bend motion without lighting up a single detector. That would mean our census of mass is off, not by a rounding error, but by enough to matter. The boldest idea goes after the rules themselves. If gravity behaves differently across enormous distances, then the pull we've been chasing might partly be an artifact of using the wrong equations at cosmic scale. Modified gravity would rewrite the math, not just the map. Each one predicts something slightly different, and that's the opening. The soonest test is already being built into next decade surveys. Start with the SKA, the Square Kilometre Array, splitting radio duty between South Africa and Australia. It's designed to catch the faint 21-centimetre glow of hydrogen in galaxies we currently can't see. That signal cuts through dust and starlight, which matters when half your map hides behind the Milky Way's own body. Then there's the Vera Rubin Observatory, sweeping the entire southern sky every few nights with a 3,200-megapixel camera. Over 10 years, it'll track billions of galaxies and watch how they drift. Feed those positions into the flow models, and the streaming pattern either sharpens or falls apart. Euclid, already launched, is measuring the shapes and distances of galaxies out to 10 billion light-years. Its job is mapping how mass is distributed on the largest scales, the very thing our attractor story depends on. If the mass isn't where we think, the pull has to come from somewhere else. Each instrument aims at the same buried question from a different angle. More galaxies, cleaner distances, a wider net cast behind the curtain. They could confirm our story or overturn it entirely. Picture the confirming case first. The new distance measurements line up with the flow maps we already have. The pull toward Norma holds, and Shapley's weight lands right where the models predicted. Every survey pointing at the zone of avoidance would tell the same story, and the basin we call home would stand on solid ground. Now flip it. Suppose the deep accounts keep raising the mass behind the curtain, or the flow refuses to slow where dark energy says it should. Then the tidy borders we've drawn start to blur, and the boundary of our supercluster becomes an argument again instead of a settled line. There's real weight riding on which way it breaks. A single clean disagreement between two methods can force a rethink of how much matter fills the sky, how fast the whole thing streams, and where the tug actually comes from. So the coming decade isn't just refining a decimal place, it's deciding whether the map holds or cracks wide open. Either way, the result reaches all the way down to you. Think about how you'd describe where you live. A street, a city, a country, a planet, circling one ordinary star. It feels fixed, like a dot you could pin down and return to. But none of those coordinates sit still, and neither do you. Right now, the ground under your feet is riding the Earth around the Sun at roughly 30 kilometers per second. The Sun is dragging the whole solar system around the galaxy at about 220 kilometers per second, and the Milky Way itself is falling through space at hundreds of kilometers per second toward that pull we've been tracing. Stack those motions together, and the number climbs past 600 kilometers per second relative to the ancient light left over from the Big Bang. You've been moving that fast every second you've been alive, and every second before that, without ever feeling a thing. So when you say where you are, you're naming a place that has already moved on. The dot slides even as you point at it, because your address isn't a point, it's a trajectory. Sit still for a second, really still. You're not moving, right? Except the ground under you is spinning at about 1,000 miles per hour, and Earth is looping the Sun at 67,000 miles per hour, and none of that is even the part that matters here. The Sun drags the whole solar system around the Milky Way at roughly 500,000 miles per hour, and the galaxy itself is falling through the dark, swept along inside a supercluster that's flowing towards something we can barely see. Stack all that motion together, and the stillness you feel is a kind of comforting lie. The porch you grew up on, the window you're looking through right now, they've never once held the same spot in space. Every memory you have happened somewhere the universe has already left behind. Home was never a location. It was a moment your galaxy passed through on its way somewhere else. We just don't feel it, because the clock is too slow and the distances too vast to notice. On the timescales involved, everything you know is a single frame. Think about the numbers for a second. The Milky Way is drifting toward the Shapley region at hundreds of kilometers per second, and it's been doing that for billions of years. A human life runs maybe 80 years. In that whole span, the galaxy moves a distance so small against the cosmic scale that it wouldn't register on any map you could draw. Every person who ever lived saw the same sky, more or less. The pyramids, the first telescopes, this moment right now, all of it happened inside one unbroken glide across the same tiny stretch of the flow. Nobody has ever watched the drift change. Nobody ever will. Not in a lifetime. Not in 1,000. So the motion is real, but it's the kind of thing you inherit rather than experience. You're born mid-current, you live your entire life mid-current, and you leave with the galaxy exactly where it was, still falling toward the same distant weight. The journey doesn't wait for us, and it doesn't slow down to be seen. Step back far enough, and the whole journey fits into a single picture. Trace it back, and it's a clean line. We started with a sky that looked calm, galaxies drifting apart at a steady beat, everything obeying the same simple expansion. That was the picture that held for decades. Then the numbers wobbled. Our own galaxy was moving 600 kilometers per second in a direction that tidy math couldn't explain. Something local was pulling, layered on top of the cosmic expansion, and it demanded a source. So the map filled in, a hidden mass behind the plane of the Milky Way, the region we came to call the Great Attractor, sitting in a dense knot of galaxies. Behind it, farther out, an even heavier crowd of clusters, adding its own steady tug. And on the other side, emptiness doing its share of the work, a vast underdense patch nudging us away instead of drawing us in. Pull from the crowded direction, push from the hollow one, all of it feeding the same drift. Zoom out, and those pieces stop being separate mysteries. They snap into one flowing shape, one continuous current with us riding inside it, which leaves the one question this whole story was really about. For decades we asked where the Milky Way was headed, as if the answer had to be a thing. Some vast clump of galaxies, some hidden mass reaching out with gravity we could name and weigh. And a lot of that pull is exactly that, the Shapley cluster, the crowded lanes of the cosmic web hauling us along. But roughly half of our motion doesn't come from anything sitting in front of us. It comes from what sits behind us, an enormous stretch of near nothing, the dipole repeller, pushing simply by having so little in it. So the real question was never which giant is dragging us home. It's whether an emptiness we can barely detect, a region defined by absence, is shaping our journey as forcefully as anything solid ever could. We spend our lives looking toward the light, toward the things that are there. Turns out the void has a say in where we go to. That's worth sitting with next time you look up. For most of human history, the sky was the one thing you could count on. The Egyptians aligned pyramids to stars that held their positions across generations. Sailors steered by Polaris because it sat still while everything else wheeled around it. The ancient Greeks built the whole idea into their physics. Above the changeable earth sat the celestial sphere, perfect and eternal, turning but never truly moving. Aristotle called those outer heavens unchanging, made of a fifth element that couldn't decay or drift. And honestly, the evidence backed them up. A constellation your grandparents saw looks the same to you. The patterns that guided a Babylonian farmer 4,000 years ago still hang in roughly the same spots tonight. Nothing you can see with your eyes suggests otherwise. The stars keep their shapes for thousands of years, and a human lifetime is far too short to catch them shifting. So the sky reads as permanence itself, a backdrop that simply is. But that stillness was never real. It was just too slow and too vast for anyone to feel. Every one of those fixed points was already racing somewhere. For thousands of years, the night sky looked like a fixed ceiling. The same constellations rose in the same order, season after season, generation after generation. A shepherd in Babylon and a sailor in Greece traced the exact same shapes, separated by centuries. That constancy wasn't an illusion of ignorance. The stars really do shift, but the nearest ones crawl across the sky by less than an arcsecond per year. Over a human lifetime, that motion is smaller than the width of a coin seen from miles away. So astronomers mapped the heavens as if they were carved in stone. They named the patterns, built calendars around them, and steered ships by points they trusted never to move. The sky became the one thing you could count on to stay put. And for the naked eye, that trust held. Nobody could see the drift, so nobody imagined it. Beneath that stillness ran currents we'd only measure centuries later. Here's what the sky won't tell you. Every galaxy you can name looks parked, fixed against the dark, going nowhere. But nothing out there is truly still. Each one is riding a slow tide, drifting hundreds of kilometers every second through space that itself is stretching. Think of a leaf on a river. From above, it looks motionless against the water around it, but the whole surface is sliding downstream, leaf and current together. Galaxies work the same way. They sit inside vast flows, and the flow carries them along without any visible push. We can't see these currents. There's no glow, no trail, nothing a telescope catches directly. What we can measure is the leftover motion, the tiny extra nudge on top of the universe's expansion. And when you map that nudge across thousands of galaxies, a pattern shows up. They don't wander at random. Whole neighborhoods of galaxies slide together, in step, like they're all obeying the same quiet instruction. Trace those currents back, and they all lean the same way. Take 100 galaxies scattered across tens of millions of light years, all in separate cosmic backyards, and something odd shows up. Strip away the expansion of the universe, subtract the tug of nearby clusters, and a stubborn leftover motion refuses to vanish. It doesn't cancel out, it points. And it points the same direction almost everywhere astronomers looked. Galaxies out toward one patch of sky, galaxies on the opposite side, spirals near us and giants far past them, all shading their velocities toward a single region low in the southern sky. Not roughly, consistently. That's the part that gnawed at people. Random errors scatter. Local pulls point in local directions. But a bias shared by objects with nothing in common, spread across a huge volume, means one thing is reaching all of them at once. For years, this lean lived in tables of numbers, easy to argue about, easy to explain away as measurement slop. The direction was there, but blurry, buried in scatter. Then someone plotted every velocity as a vector on a single chart. One map turned that lean into a hard, undeniable arrow. So picture the arrow. It starts at the Milky Way and points toward a spot in the southern sky, near the border of Centaurus and Hydra. Every galaxy in our neighborhood shares that same lean, all drifting the same way, like they're caught in a current none of them chose. And the arrow isn't a suggestion. Our whole local group is moving at roughly 600 kilometers per second relative to the leftover glow of the Big Bang. That's about 1.3 million miles an hour in one fixed direction without pause. When you overlay that vector on a sky map, it stops feeling abstract. You can trace it with a finger. It cuts across familiar constellations and heads for a single region, as if something out there had set the destination long before we ever looked up. But here's what makes the arrow uneasy to follow. It doesn't point somewhere we can see clearly. It points at a stretch of sky we've spent decades struggling to look through. Following that arrow leads straight into forbidden territory. The problem is our own galaxy. The Milky Way's disk wraps around us like a wall, packed with dust and stars so dense that light from behind it barely gets through. Right along that band, roughly a fifth of the entire sky goes dark to us. Astronomers call it the Zone of Avoidance. And of all the places the arrow could point, it points there. The thing tugging on us sits low, tucked behind the thickest part of that curtain, in the direction of the constellations Norma and Centaurus. We're being pulled toward a region we physically cannot see. For decades, that band was just a blank on the map. Optical telescopes hit the dust and stop cold. Whatever mass lives back there, whatever is doing the pulling, stayed hidden in the one direction we most needed to look. So the answer was buried in the worst possible spot. Only a few daring surveys ever charted what hides in there. So teams went hunting with the only tools that could see through the dust. Radio telescopes don't care about visible light, so they picked up the hydrogen gas swirling inside galaxies we couldn't otherwise spot. The Parkes dish in Australia ran a blind survey across the plane of the Milky Way, listening for that faint 21-centimeter signal, galaxy by galaxy. Infrared campaigns pushed from the other side. Dust glows in the infrared and lets longer wavelengths slip past. So surveys like 2MASS and later scans mapped heat where the eye saw only black. Bit by bit, galaxies started popping out of the murk, ones nobody had catalogued before. What came back wasn't a smooth scatter. The hidden galaxies clumped together, tracing structures that clearly continued straight behind the band we couldn't see. Cluster after cluster surfaced, each one adding a little more mass to the ledger. And as the maps filled in, one thing stood out. The most important find sat almost exactly on the arrow's line. Line up the surveys, and the picture gets almost too clean. The Norma cluster sits right in the path our galaxy is traveling, buried behind the Milky Way's dusty plain, exactly where the motion vector points. It's not alone out there. A whole family of galaxy groups clusters around it, strung along the same direction we're being pulled. So astronomers did the obvious thing. They added it up. Every group, every cluster tied to that region, all their mass tallied into one running total and set against the arrow's demand. On paper, it looks like a match. The biggest concentration of galaxies in that swath of sky lands within a few degrees of where the pull comes from. The direction fits. The rough location fits. For a while, that felt like enough to close the case. But the numbers kept nagging. When you weigh Norma and its companions carefully, the gravity they can produce falls a step behind the speed we're actually moving. The arrow points there. The mass is there. And still, the mass on that line wasn't enough. So the astronomers ran the tally again. They added up every galaxy along that direction, every cluster, every wisp of gas the telescopes could catch. The Great Attractor region held a serious concentration of mass. No argument there. But the pull it should have produced fell short of the pull we actually feel. The numbers kept coming up thin. Estimates put the attractor's mass at tens of thousands of galaxies worth of material. And that sounds enormous, until you measure the speed it's supposed to explain. Our whole neighborhood streams at around 600 kilometers per second. To yank us that fast, something needs more heft than the local count could deliver. You could shift the error bars, tweak the distances, recount the faint stuff hiding behind the galactic plane. It narrowed the gap a little. It never closed it. The tug was real, the source was partly visible, and the arithmetic still refused to balance. That leftover force had to be coming from somewhere farther out, something bigger, sitting deeper in the same line of sight. Closing the gap meant looking far past our own supercluster. So astronomers pushed the map outward, past the edge of Laniakea, into the deep background where galaxies get faint and catalogues run thin. At those distances, individual galaxies stop mattering. What you're tracking are whole clusters, each one holding hundreds or thousands of galaxies bound together by gravity. The trick was velocity. Every one of those distant clusters carries a redshift, and buried inside that redshift is a small extra push that doesn't match pure expansion. Line up enough of them across the same patch of sky, and the leftover motions start pointing the same direction, like compass needles feeling the same distant north. When they added up the mass in that direction, out to 600 million light-years, the numbers finally started to move. Concentration after concentration stacked along the same sightline, each one adding a little more pull to the ledger. But the deeper they looked, one region kept swelling, denser and heavier than anything between us and it. One deep structure dwarfed everything closer to home. That structure has a name, and by now you know it: Shapley. Sitting roughly 650 million light-years out, it packs together more than 8,000 galaxies into a single overdense knot. Nothing else in this part of the universe carries that kind of weight. When you trace the streaming of galaxies past the Great Attractor, the flow doesn't stop there. It keeps leaning outward, past Norma, past the wall, aimed at that far heavier mass sitting behind it. The closer regions give us a shove. Shapley gives us a haul. It's the reason the numbers behind the Great Attractor never fully added up on their own. The pit we sit in was real, but it was always just the near edge of a much deeper slope. The real anchor was farther out, quieter, and vastly more massive. So the ledger tilts hard in one direction, one enormous concentration doing most of the pulling from beyond our own borders. But a draw this strong needs something opposite to balance the books. Here's what closes the account. On one side sits that distant mass, reeling us in. On the other sits emptiness, a region so underpopulated that it can't hold on to anything. Underdense space behaves like a slope tilted the wrong way. Matter drains out of it toward denser neighborhoods, and anything nearby feels a gentle shove away from the hollow. So the void doesn't tug at all. It effectively pushes, and that push points the same way the far-off pull does. Line those two effects up, and roughly 630 kilometers per second of the Milky Way's motion starts to make sense. A chunk comes from being drawn toward the crowded side. A chunk comes from being nudged off the empty side. Add them, and they don't fight, they reinforce. That's the part that stops you. A giant overdensity in one direction and a giant absence in the other, working together, aimed almost perfectly along a single line. The symmetry that emerged was almost too neat to be accidental. And that's exactly when a scientist should get nervous. When a picture lines up this cleanly, when the numbers slot together and the arrows point the same way, the instinct to celebrate is the wrong instinct. Nature rarely hands you a story this tidy without a catch hiding somewhere in it. Because the human brain is built to find patterns, even in noise. Stare at scattered data long enough and you'll see a face, a line, a design. The push from behind and the pull ahead balanced along one axis, that could be the real geometry of our corner of the universe. Or it could be the shape we wanted to see, dressed up in decimal places. There were real reasons to worry. The measurements carry error bars. The maps have gaps. The direction of the Milky Way's motion is one thing, but pinning what drives it and how much of it leaves room for a story to fill in the blanks a little too conveniently. So the balance couldn't just be admired, it had to be attacked. Rigorous tests were run to make sure we weren't fooling ourselves. Start with the ugliest suspect, selection bias. When you map galaxies, the bright ones jump out and the faint ones hide. So a survey can invent a crowd where there's really just a well-lit few. Teams reran the flow measurements waiting for that, cutting the visible galaxies and asking whether the pull toward Norma still pointed the same way. It did. Then came the instruments. Different telescopes, different filters, different decades of calibration, all carrying their own small lies about distance. So the same patch of sky got measured with separate methods. Tully-Fisher on spiral rotation, surface brightness on ellipticals, and the results were stacked to see if they'd disagree. They mostly didn't. Where they drifted apart, the gap sat inside the known error bars, not outside them. Researchers also flipped the math, feeding in random motion instead of real motion, to check whether the signal survived pure noise. It didn't, which is exactly what you want a fake pattern to do. One by one, the ways of being wrong got closed off. The checks held, and confidence in the picture climbed sharply. By the mid-2010s, the same shape kept showing up no matter who ran the numbers. Independent teams, different telescopes, different corrections for the dust in the plane of the Milky Way, all landed on a flow toward Norma, with the Shapley concentration pulling from farther out. When separate methods agree without coordinating, that's the closest thing astronomy has to proof. The velocity maps built from thousands of galaxies traced the same currents. The gravity that should exist, given all that mass, lined up, roughly, with the motion we actually measure. The repeller on the far side pushed, while the attractors pulled, and the arithmetic of push and pull covered most of what our galaxy is doing at 600 kilometers per second. Reviewers who'd spent careers doubting flow measurements started citing the framework instead of poking holes in it. The model wasn't just surviving anymore. It was becoming the default assumption, the thing you built on rather than argued against. Yet one loose thread refused to be tied off. Add up every pull we can name, and the numbers almost close. The Great Attractor tugs, the Shapley Concentration tugs harder from behind it, and the dipole repeller shoves from the empty side. Stack those forces together, and you recover most of the 630 kilometers per second our galaxy is actually moving. Most, not all, depending on which survey you trust and how deep it reaches. Somewhere between 10% and 30% of that motion still has no clean address. It's a small residual, easy to wave away as measurement noise, or a survey that didn't peer quite far enough. But the excess keeps showing up. Push the maps deeper, past Shapley, past the voids we've charted, and the leftover velocity doesn't shrink the way a rounding error should. Something out there, farther than our best catalogs reach, seems to be adding its own quiet vote. Cosmologists have a name for that discomfort. It's the flow that survives every accounting, the piece the standard picture can't quite absorb. That thread ties directly to the biggest reveals still ahead. So walk back through what we've stacked up. The velocities that refuse to cancel out. The pull toward Norma that measured real, then measured short. The mass we counted, and the mass we couldn't find, no matter how deep we looked. Each piece arrived from a different instrument, a different decade, a different team that had no reason to agree with the others. Redshift surveys, peculiar velocity maps, the slow, stubborn arithmetic of dark matter halos. And yet they kept sliding toward the same corner of the sky. That's the part that should unsettle you. Independent measurements don't usually line up this cleanly unless something real is sitting underneath them, something with enough gravity to bend the motion of everything for hundreds of millions of light years. We've been circling it this whole time, naming the symptoms without naming the cause. The wobble, the streaming, the leftover flow. Now the circle closes. Everything we've gathered points at a single, staggering conclusion. Line up the numbers and they stop fighting each other. The Milky Way drifts at roughly 630 kilometers per second against the cosmic microwave background, and for decades we blamed the Great Attractor sitting about 150 million light-years out in Norma. But the arrows never quite balanced. Norma's pull only ever accounted for maybe half our motion. The rest kept pointing straight through it, towards something farther and heavier hiding behind the same patch of sky. So the picture reassembles in layers. A local tug from Norma, a deeper draw from the Shapley Concentration, that dense pileup of thousands of galaxies some 650 million light-years away. And on the opposite side, a region shoving instead of gripping, adding push to the pull. Stack all three and the vector snaps into place. Not one culprit, but a chain of them, working the same direction across 500 million light-years. The flow we measured stops being a mystery and becomes a map. Every thread we followed lands on the same coordinates, and with the next piece, the image we opened on finally clicks. So here's the detail that ties it all together. The pull towards Centaurus isn't one object grabbing us. It's the slope of a whole region, the Great Attractor sitting in the low ground of Laniakea, with Shapley's mass leaning on the far side and the dipole repeller pushing from behind. When you add those forces up, our motion falls out cleanly, roughly 630 kilometers per second, aimed exactly where the maps said it should be. The Milky Way isn't being dragged to a destination, it's rolling downhill along a valley 500 million light-years wide, and it always will be, because dark energy will stretch that valley apart before we ever arrive. We started with a single arrow on the sky and no idea what it meant. Now we can name every hand on it, a basin, a giant, a void, and an expansion that guarantees the trip never ends. The real question isn't what's pulling us, it's whether anything out there is standing still at all. If that keeps you up at night, stick around, there's a lot more sky to cross.